Hi everyone, my name is Vasu Vikram and I'm excited to present growing a test corpus using Bonsai Fuzzing. So we're focused on automatically generating a test corpus with concise inputs. And we specifically walked through an example of applying Bonsai Fuzzing to a compiler designed for education so we can provide meaningful test cases for students to use as they are developing their compiler project. So they can use these test cases as a partial specification for their project. And so I'd like to first talk about a little background of the language of ChocoPy. So ChocoPy is a statically typed dialect of Python 3.6. I've included an example of a ChocoPy program here where we have a function contains, it has type annotated parameters, items, and x, and it has a specified return type Boolean. And so if you read through this program, it follows natural Python syntax, and this program is actually a valid Python 3.6 program. And so ChocoPy was designed for the purpose of teaching undergraduate compiler courses. In these courses, students are tasked with developing a project, a compiler project that converts ChocoPy programs to RISC-V assembly. And a little bit more detail on these ChocoPy-based courses, the infrastructure is set up so that each of the student and reference implementations takes in a test suite. So each of the programs in this test suite, ChocoPy programs, are run through each of these implementations, and then the outputs are asserted to be equal. If the outputs between the student and reference implementations are equal, then the test case passes, otherwise it fails. And so one detail about the infrastructure is that it requires the instructors to handwrite this test suite. So the instructors need to decide what sort of programs and how they need to write these programs in order to create a good test suite for students to use. And so our question today is how do we actually automatically generate such a test suite? And so what we first need to answer is, what do we want from this test suite? And so two sort of qualities of a desirable ChocoPy test suite would be, first, that the test suite is comprehensive. So that means that across all the programs in the test suite, we cover all the language features of ChocoPy that we would like to test. The second quality is that each of the test cases in the test suite is concise. And that means that the test cases are small in size and therefore more readable, more interpretable for the students to use as they're developing their project. And so here's an example of a handwritten test program. And we can see that this is an example of a concise while loop program, where it is very clear that the while loop is the language feature that is being tested, and it's fairly small in size. And so one approach to automatically generating such a test suite is we could look at fuzz testing, where we essentially create a ChocoPy grammar sampler and use that as the generator for coverage-guided fuzz testing. And what we see is that we're able to generate a test suite that achieves high coverage. But then if you look closely at the actual test cases, we see that the programs are fairly messy, fairly large, and it's not really clear what is being tested. So in this example, we have a while loop with a nested for loop, a list expression with an if-else expression. So obviously this program is not desirable for conciseness. What we can do is we can take this fuzz testing output corpus and then apply minimization techniques such as delta-debugging or other reduction tools. And what we're able to see is, for the example that I just showed, we're able to reduce this example a fair amount. But we still see that there are still multiple language features that are being exercised in this program. We still don't really know what is being tested. We still have this while loop, for loop, if else expression. And so here's where we introduce Bonsai Fuzzing, where the key idea is to grow the test corpus from the bottom up. And in order to achieve this goal, we need to first define two things. The first one is a method of size bounding the grammar fuzzers. So what does this actually mean? We can take our grammar sampling algorithm for ChocoPy, and what we want to do is restrict the input space of programs that get generated. So we essentially want to create a size bound for the programs that get sampled from our grammar sampling algorithm. And then once we have this notion of bounding the grammar fuzzers, we can define an iterative deepening procedure to increase the size. And so this is where the idea of growing the test corpus comes in. We start off with the smallest grammar-based fuzzer that is bounded by the smallest possible bounds. And so those types of fuzzers will generate very small, very concise programs, but they will not be able to achieve high coverage since the size is very small. And then with this iterative deepening procedure, we're able to gradually increase the size of our fuzzers and therefore also increase the size of our test corpus while maintaining the notion of conciseness, since we're starting from the smallest programs. And once we have these size-bounded grammar fuzzers and we have an ordering on top of these fuzzers, we can construct a lattice that looks like this. So in this case, we have a Bonsai fuzzing lattice, in which case we can see that the 3 parameters that are used to bound the size of our grammar fuzzers are shown as the subscripts of each of our fuzzers f. So at the bottom is f111, which designates the smallest possible size-bounded grammar fuzzer. And so f111 will essentially generate very concise inputs, very small inputs. And so when we look at the Bonsai fuzzing procedure, here's how it goes. We start off by running f111. So we are running our smallest possible grammar fuzzer with coverage-guided fuzzing. And we generate inputs that look like this. We have very small inputs, such as a single pass statement, simple assignment statement, a very small function definition. And these inputs are very concise, but they're not able to achieve very high coverage. So then we take the successors of f111, which are f211, f121, and f112, and we use the output corpus of f111 as the seed inputs to each of these following fuzzers. And what that allows is we're able to start off with a seed pool of very concise inputs and mutate them to a slightly higher size, since these fuzzers are able to sample slightly larger programs. What we end up is with programs that are still concise, but they exercise more language features, such as like classes with attribute declarations or indexing or more complicated function definitions. And then finally, once we get to the top, which is f222 in this example, our final output corpus of Bonsai fuzzing is the output of f222. And we can see from these programs that we achieve much more complex language features, such as object instruction with attribute assignment or nested functions. But we're still able to maintain this conciseness because we are still mutating the seed pools from before, which were originally concise. So we're able to achieve this notion of conciseness by growing the test corpus, and we can sort of see the evolution of the programs as we're going through each of these intermediate nodes. And so when evaluating conciseness, we took the average, we took the test case size of each of the individual test cases of Bonsai fuzzing compared to baselines of the fuzz-then-reduce approach, which runs a maximum bound grammar fuzzer and then applies different reduction techniques. And we see that Bonsai fuzzing is able to achieve a 42 to 44% reduction in chocolate programs. We also evaluated it on the Google Closure compiler, which takes in JavaScript programs, and we're still able to see a reduction in those as well. Now, a natural question is, given that these programs are much smaller in size, are we able to still achieve the comprehensiveness or coverage as the baseline? And the answer is yes. We see very similar branch coverage when looking at the ChocoPie and Closure targets. So with Bonsai fuzzing, we're able to achieve this comprehensiveness even with these much more concise test inputs, which is great. And so yeah, this is Bonsai fuzzing. We showed how we're able to grow the test corpus to achieve this notion of conciseness. And so feel free to check out our GitHub for Bonsai fuzzing. It has example corpuses that you can look through to see generated programs for Bonsai fuzzing for ChocoPie and Closure. And feel free to email me, Rohan, or Kaushik, and I'm very happy to answer any questions. So thank you very much. I'm happy to answer any questions now, and have a good one.
Okay, we are live. Hello, everyone. Welcome to the last paper on fuzzing. We have Vasu here, one of the authors with us, and he can take questions. And I already see a couple of questions. The first one is coming from Rui. He is asking, are you only looking at branch coverage?
Yeah, so for what we measured in Bonsai fuzzing, the main measurement we looked at was the average test case size in each of the corpuses with the Bonsai fuzzing corpus output and the baseline output. And then we also measured branch coverage to ensure that the Bonsai fuzzing corpus, even though the test cases are generally smaller in size, would achieve the same amount of coverage. And in addition to that, we also measured semantic validity. So we basically looked at the percentage of programs in the corpus that were semantically valid, since generally we prefer semantically valid programs to be a representative test case for each of our language features that we wanted to test.
Okay, thank you very much. And Michael is asking, does the lattice represent some notion of tested language features? For example, if I only care about testing programs with functions and while loops, can I get corresponding programs by focusing on a specific lattice element?
That's a good question. So what the lattice represents is we have in our Bonsai Fuzzing lattice, we had a set of 3 parameters that were used to bound the size of our input space. And so those were the subscripts that were shown in each of the lattice elements. So F111, for example. And it doesn't, each node of the lattice doesn't represent a specific language feature, but it represents a specific subset of the input space. So in F111, specifically what these parameters were doing were bounding the size of the extended EBNF grammar that that defines ChocoPie. And so F111 was limiting essentially the space of programs that our fuzzer was sampling from. So if we wanted to test specific, if we wanted to generate a corpus with much smaller programs, then we would choose nodes that are earlier in the lattice. But it doesn't necessarily control exactly which language features are being sampled.
So you could you generate a subgrammar for the exactly language features that you're planning to test and then use the same approach?
Yeah, so you could basically modify the generator or the grammar sampler to limit the language features that you're testing. Yep.
All right. Thank you very much. And Na is asking, for the lattice structure, if an input is an integer or floating point number, the search space can become huge, right? How do you deal with such scenarios?
So for the lattice structure, it's defined by essentially the partial ordering that we have that is given by these parameters. So in our example of the Bonsai Fuzzing lattice, we had 3 parameters and our maximum bounds was 333. And so you are correct that when you extend this maximum bound of 333, the lattice can become much larger and essentially explode. But what we found in our paper was that a maximum bound of 333 is able to generate programs that achieve high enough coverage that we do not need to extend the bound beyond that. So in our case, we found that these programs that were bounded by that maximum size are generally good enough to cover all the language features that we desire.
Okay, thank you. I'm not seeing further questions, but I want to ask you one. So your main use case was for generating inputs to test compilers, right? Mm-hmm. And I'm wondering whether you ended up using this approach in the compiler course to assess student submissions, and was it successful?
Yeah, that's a good question. So we unfortunately were unable to run our resulting corpus on the actual student assignments due to some procedural issue with using the assignments. But I'm starting my PhD soon, so I definitely want to try this. And we used mutation fuzzing as a sort of substitute for this approach since they were somewhat correlated. But yeah, this is definitely an approach that I want to take in the future.
Then what is the next use case that you will be looking at, the next application?
Yeah, that's a good question. So I think Bonsai Fuzzing, since we're sort of synthesizing this test corpus, I think a good use case would be regression testing. So generally when you have a fuzzer, you could either have some software, and then when you're testing a change or whatever, you can run the fuzzer for an extended amount of time. Eventually, you'll find bugs. But in the case of a regression testing suite, it's much more concise and much more readable, which is the point of Bonsai Fuzzing.
All right, thank you. We have a question from Burju. First, she's thanking for the great talk. And the question is, how do we decide we have sufficiently explored the set of behaviors at a level and move up to the next level of the lattice?
Yeah, great question. So for Bonsai Fuzzing, we assigned a time limit to each of the nodes in the lattice, and we decided on 1 hour of fuzzing for each of the nodes. And we chose 1 hour as a conservative approach to, since 1 hour essentially ensures that all of the fuzzing is saturated, the coverage is saturated during that fuzzing session. And what you could do on top of this approach is you could optimize and basically measure the coverage during the fuzzing session online. And once it's sort of saturated, you can then stop the fuzzing session. So that would be an optimization on Bonsai Fuzzing, but we specifically chose 1 hour per node as a more conservative approach.
Okay, thank you. Do you have any follow-up questions? Anybody in the audience? We have a few more minutes left. There you go. We have a question from Rohan. For context about the class, when this research was done, oh, it's a comment. Okay, so
yeah,
is
Rohan
this one of your co-authors? Okay.
Yeah, exactly.
All right. Was it what? Let's see. When this research was done, Vasu was an undergraduate student in the compiler course and was fuzzing his own assignments. I see. All right. So that was an explanation to my question.
Yeah, exactly.
All right. In that case, we have another 2 minutes to go, and after that, the system will ask everyone if they want to move on to the discussion group, where it will look like a regular Zoom session, and it's free for all. So I suggest that you stay on for another 2 minutes, and I will leave the room soon and maybe meet up with some people who were asking questions in the discussion room. But other than that, so the fuzzing session is over. We had 3 great papers. Let's give it up virtually for Vasu. And we'll see you in other sessions of the conference soon.
Thank you, everyone.
Thanks, everyone. Okay, Vasu, I'll leave the room and check my next backstage. Okay. See you around.
Good.
Yeah.
Thank you.